Hi everybody. In this video we're going to apply the method of separation of variables to the one-dimensional Schrodinger equation. So in this equation, capital Psi is the wave function, capital V is the potential energy function. We have here a second partial derivative with respect to x. Here we've got a first partial derivative with respect to time. So this is known as a partial differential equation because we've got partial derivatives with respect to two different variables in this equation. Now so we're going to try and solve this equation using separation of variables. And solving a partial differential equation means breaking it up into separate equations involving only x and only time. So we'll see how that plays out in just a moment. Now, this differential equation involves derivatives with respect to position and time. So in general, we should expect our wave function to be a position of both position and time. The separation of variables method involves trying a provisional assumption that those dependencies on position and time, for example, are separate. So in other words, it involves an assumption that our overall solution that we're looking for, the wave function, has a part that we can basically factor the position and time dependencies out. So that this overall function will be a product of two functions, one which depends on x, one that depends on time. Now it becomes cumbersome to write explicitly out this time dependence everywhere, so just keep in mind in what follows that capital Psi is something that depends on both position and time. Lowercase psi just depends on x. This lowercase phi depends only on time. So I'll write that separation of variables this way. All the position dependence is carried here, all the time dependence is carried there, and this thing has both position and time dependence. Okay, here we go. So let's take this and shove it into here, and shove it into the Schrodinger equation. Substituting this everywhere for capital Psi in the original Schrodinger equation gives us this expression. Now we can do some factoring here. For example, this is a derivative with respect to x. Little psi depends on x, but little phi does not. So little phi, which does not depend on x, can come out of this derivative because with respect to the variable of differentiation here, this little phi is a constant. Likewise, here we have a partial derivative with respect to time. Little psi, which depends only on x, spatial variable, is constant with respect to this variable time. So we can take the psi out of this derivative. And that gives us the following. So from here, the phi has come out. From here, the psi has come out. Now, the next step, which is often a common step in any separation of variables way to attack a partial differential equation, is to divide everything through by psi phi. So let's do that. So I've rewritten all this in the black and showed the division by little psi phi in the red. And we see here the phi's cancel. Both the psi's and the phi's cancel here, and here the psi's cancel. So this equation simplifies quite nicely. So now look what we have. On one side of the equation, we only have constants, stuff that depends on x, like this, and derivatives with respect to x, and we'll provisionally assume that this potential energy function depends only on position, not on time. And on the right-hand side, we have only stuff that depends on time, or else stuff that's constant. There's constants. This is a function that depends only on time. Here we have a partial derivative with respect to time. So we have a side that depends only on space, a side that depends only on time. That is, we have separated the space dependence from the time dependence. And that, in addition to the initial attempt to factor the position and time dependence, is what gives this technique its name, separation of variables. Now, here's something interesting that comes up in these types of situations where you've got space dependence, or dependence on one variable on one side of an equation, and dependence only on another variable on another side of the equation. It turns out both sides of the equation are equal to a constant. And let's see how that works out. First, let's look at the right-hand side, which depends only on time. Now, I could fiddle around with the position dependence. Remember, the original wave function is supposed to depend both on position and time. So I could change x all I want, but this side doesn't depend on x at all. So this side is entirely independent of x. I could change x to my heart's delight, but that has no impact over here because this side doesn't depend on x at all. So fiddling with variables over here has no impact on over here. So this side must be equal to a constant. On the other hand, you could turn all that around and say, well, let's consider the left-hand side. The left-hand side depends only on space. I can go and change time all I want, but that'll have no impact on this over here. So this side must be equal to a constant. So both sides must be equal to a constant, and of course it must be equal to the same constant. Let's call that constant E. So that gives us the following two equations. There's this one here, which depends only on space. This is known as the time-independent Schrödinger equation. To get any further on solving this equation, we need to know the functional dependence, how this potential energy function specifically depends on position. Otherwise, we can't go any further with that. And at upper-level quantum mechanics often boils down to taking a particular form of the potential energy function and then solving this equation. And we'll do that a little bit later in another video. The other equation is just this time-dependent equation, and we can actually solve that pretty easily, and we'll solve that in the next video. Before doing that, a couple remarks are in order. First, at this point, this E is just some constant, which we call in this method the separation constant. It turns out that, for reasons that I'm going to not go into in this video, that this E turns out to be the energy. We're not going to show that here, but it can be shown. So I'm not going to show that step to show that E is actually the energy. We'll just assume that it can be shown, and now we'll take this separation constant to be the energy. I want to make one final comment relating to the derivative notation. In our original equation, we have partial derivatives because this state function depends on both position and time. So when we take derivatives, we're taking derivatives with respect to one or the other. We need a partial differential notation. So that's what this little scripty d is. But after we've finished our project of separating variables in this expression, we now have an equation here that depends only on x, for example, and one here that depends only on time. So let's look at the x one. In this x equation, the little psi depends only on x. There's no time dependence. So we don't have to distinguish between the possibility of taking a derivative with respect to x and taking a derivative with respect to time. This little psi has only x dependence, so we can write this derivative as a full derivative with respect to x. So that's what's going on here when we change these little script d's to these little full d's. It simply reflects that in these equations, each of them has only dependence on a single variable that we're taking derivatives with respect to. And so we can write those respective derivatives as full derivatives. So, applying separation of variables to the original Schrödinger equation, and separation of variables meaning taking this thing that depends on position and time and assuming that the position dependence and the time dependence can be factored into separate factors, we reduce the original Schrödinger equation into this, which we call the time-independent Schrödinger equation, and then this time-dependent piece. So let's solve the time-dependent piece. And again, we're taking for granted now that it can be shown that this E is the energy. So let's take a closer look at this equation. We have a dependent variable, phi, and an independent variable, t, and then a bunch of constants. So and we have this first derivative here. So we have a first order differential equation. It's pretty simple. Differential equations like this can be solved by basically getting all the phi stuff, for example here, separated from all the t stuff. That is, separate the dependent variable from the independent variable. Interestingly enough, this solution method for this type of equation is also called separation of variables, but we shouldn't confuse that with the separation of variables method for solving a partial differential equation. So I'm going to call this separation of variables junior. So let's multiply both sides by dt, divide both sides by IH bar, and we get. And to go from here to here, we just note that 1 over I is equal to minus I. So now we have all the phi stuff on one side, all the t stuff and constants on the other side. So let's integrate both sides. And then we can take both of these indefinite integrals. The integral of the left-hand side just gives us the natural log of phi. The integral of the right-hand side, we note that minus IE over h bar is just a constant, so that comes out. So we just have the integral of dt, which gives us t. And these are indefinite integrals, so we need to put a constant here. To get rid of this natural log, we could put both sides in the power of an exponential function. On the left-hand side, e to the natural log of phi is just phi. That's the whole reason we put both sides in the power of an exponential. On the right-hand side, I've used the fact that e to stuff plus other stuff, or e to the a plus b, is just e to the a times e to the b. So e to the minus IE over h bar t plus c becomes e to this part times e to this part. And we can rewrite e to the c as just another constant. Let's call that constant a. So now finally we've solved our time-dependent equation for phi and gotten a solution for that. So let's take stock of where we are. In our original Schrodinger equation, we had capital psi, which could depend on position and time, and we tried a solution in which there was a space part and a time part that were separated out. So now we've actually solved the time part of this original Schrodinger equation, and we were able to do that without really assuming anything about the physical problem. So this gives us information about how the time part of these product solutions evolves. So now let's put all this together. Our overall wave function, capital psi, is composed of a space part and a time part. We have a solution for the time part right here, so let's put this together. So we can write it like this. Now we're going to make one more simplification step. Our overall wave function needs to be normalized. What we're going to do is we're going to take this constant a and put it in with the spatial part of the state function. And so we're going to let the spatial part of the state function carry all the burden of normalization, so to speak. So by letting the spatial part of the state function absorb this a, and then ultimately requiring that this overall state function be normalized, we can just write this more simply, and it leaves us with this expression here. Now we have a couple more very important details. First, in this overall solution for our overall wave function that has both position and time dependence, we don't have an expression yet for the position dependence. We need to go and solve the time-independent Schrodinger equation to get that. And in order to do that, we need to know the specifics of the potential energy function involved in the problem of interest. So we'll put that off for later. But there's something else we have to consider that's just as important. In our initial move to use separation of variables to take the original Schrodinger equation and to break it into two equations, one that depended only on space and another that depended only on time, we introduced this separation constant, E, which I've argued can be shown to be the energy. But there's nothing in anything we said that said that there could only be one such constant that would allow these equations to be true. In fact, it turns out in general there can be many constants. For example, in bound quantum mechanical systems or problems such as the quanton in a box, the simple harmonic oscillator, and the hydrogen atom, we have certain allowed energies, call them E sub n, with corresponding energy eigenstates, psi sub n, where n can be 1, 2, 3, etc., or in the case of the simple harmonic oscillator, we also have an n equals 0 state. So, putting it all together, for bound state problems like the quanton in a box, the simple harmonic oscillator, the hydrogen atom, there could be lots of different values of E for which these things have solutions. Call them E sub n. So if you have a particular E sub n, a particular separation constant, we'd have it here and we'd have it here. This time-independent Schrödinger equation, which we haven't solved yet, but if we knew the potential energy function, we could get the corresponding psi sub n, the energy eigenstate corresponding to energy E sub n, but there would also be a corresponding value of phi that would solve this equation with E sub n here as the separation constant. We could call that phi sub n, I won't put it here, and that would have an E sub n right here. And so putting all that together, our overall solution for our product solution, the thing that depends on both space and time, we'd have capital psi sub n, depending on position and time, would equal the energy eigenstate, little psi sub n, times this exponential function which has E sub n in it. Now, at time t equals 0, we'd have e to the 0, which is 1, and this thing, which in general is capital psi sub n, the state function overall of position and time, well, at time 0, we would just have this times e to the 0, which is 1. To put it another way, if we know our state function at time 0 is one of the energy eigenstates, then we can immediately know that its state at time t will be that energy eigenstate times this e to the minus I e sub n t over h bar factor, where e sub n is the energy corresponding to this energy eigenstate. In the case of unbound problems, instead of having just particular values of E, these E sub n's that would be allowed, there could be a whole continuum of them. And so we'd have something similar, except that instead of just having discrete values of E sub n, we just have a whole continuum of things like this. Finally, there's one more thing we have to consider. In general, a quantum state can be a superposition. So, for example, if one of our bound state systems has an initial state function that is a superposition of the energy eigenstates, then applying the superposition principle in combination with this time evolution rule, where each of these energy eigenstates will evolve like this, then the quantum state at time t will be just this superposition here. In short, if we can write our initial state function as some superposition of the energy eigenstates, then we can immediately, using the superposition and the time evolution principle, write down the state function at time t. So this combination is very powerful.